Great. Okay. Thanks everyone for coming back to this afternoon session. For the first talk this afternoon, we're looking at deep learning and uncertainty, and looking at a particular tool called Edward2, which is, like, I guess most of you probably have heard of and might have used. And Dustin Tran and Zachary Nando from Google Brain will be discussing this and explaining how to use it and so on. Yeah, over to you guys. Thanks.
All right. Thanks, Michael, for the introduction. So yeah, my colleague Zach and I will be talking about some work we've been doing at Google toward reliable deep learning, more specifically toward better uncertainty quantification, toward better robustness properties, and in particular, the sort of infrastructure that we've been developing to accelerate that research workflow. So just give a sort of rough overview of like folks that have been working on this within Google. I think over the past year to past 2 years, we started assembling a team around just this sort of topic. I try to identify the key strategic areas where this has important benefits at Google in specific products, on specific research challenges, and I think we're making a lot of really nice progress, in particular with a lot of collaborators involved. So the work I'm presenting is really just sort of a collection of progress made by all of these folks here. Okay, so starting from just like a motivation, high-level review, the work that we've been focusing on most of the team has really been about this one team mission, which is developing models that know what they don't know. It's sort of a broad requirements, but there are a lot of different things that we might require about having these particular models that are explicitly knowledgeable about what particular predictions that they might be having. So this ranges from things like robustness to distribution shift. So you're actually querying about inputs that might change over time. You're asking questions about the actual uncertainty outputs. So instead of just having class outputs that you're using for particular prediction for, say, a classifier, you're using, say, the uncertainty output. It might be the softmax probabilities for a classifier. It might even be some inherent internal state of your model. And you're using that to actually perform some different decisions. And why might we care about reliable deep learning? Well, here's a very simplistic scenario that comes from our NeurIPS tutorial last year. So here, what we're doing is looking at a very synthetic data set. This is taking ImageNets, and the data set is known as ImageNet-C, ImageNet corruptions. And there, what they do is they have a bunch of synthetic image sort of perturbations. So they might add things like speckled noise, filtering, different random cropping, all that sort of stuff. And what we're trying to evaluate is how well the model performs as a function of the intensity of the shift. So in these evaluations, it's not a typical sort of IAD setting where your test distribution is equivalent to whatever you're training on. Instead, there is a quite drastic shift, and there's a specific magnitude according to the amount of, in this case, the amount of transformation you're applying. So here, the amount of speckled noise you're adding to a frog image. And what we find through a lot of different works that we've been doing is that accuracy of these models does degrade over time quite drastically. And that's not unexpected. But the surprising thing is that you would hope that the models don't know that therefore, at higher and higher intensities. But we actually do find that the calibration error of these models, which is sort of an assessment of how good the uncertainty estimates are, they actually do degrade over time over the dataset shift as well. So the models are not only not very accurate, not very robust, but they're also not very uncertain. So there's certainly work to do even in this sort of synthetic ImageNet setting. To tie this back to maybe specific applications, so one product that we've been working with has been with the Google Health division, and example is to the left figure here. So Here you might be using sort of like a neural net to take in as input a collection of different patches of skin. So you're trying to do this for diagnosing skin conditions of particular patches. And the model is outputting some set of classes for what's most likely, what that skin condition is most likely. However, there is a huge amount of diseases, a lot of different phenomena that may actually be dependent on different aspects of the input images that you're putting in. And a big component of it is being able to say that I don't know, that the model either is trying to make a prediction about a condition that it hasn't actually trained on. So it's sort of like beyond the K different training classes that it does have available data on, or it might even just defer to the prediction and say, hey, I just don't really know. I'm not really confident about this particular prediction. And another example, what we would like is having predictions that are really balanced across different subgroups. So in another example, we applied uncertainty modeling to electronic health records, and what we found was that across different age groups as a particular demographic, the quality of the model that you're getting differs quite drastically across your age group. And ideally, that's not the case, that you would have a bit more fair predictions. And those are sort of two different examples of instantiations of the tasks that we care a lot about. More broadly, there's a huge landscape of tasks. So here I'm just noting down sort of like 6 different tasks that you might be thinking of in sort of abstract sets. They range from areas with selective prediction, where you're using the uncertainty to trust, where should I trust the model prediction? The open set recognition, which was the dermatology application, where you're taking inputs and the training classes you're trying to output may not actually, the inputs may not actually belong to one of those classes. There's sequential decision making involved. So even if you don't care about using the specific uncertainty, it might be implicitly part of an overall objective to get a better reward, or to minimize the number of examples to get a target metric like in active learning. And this goes on and on. There's different applications for all of these that we've been focusing on. But I won't touch too much on all these different aspects. Just to give a sense of how we've been approaching this these sort of challenges, well, one that is taken from our NERPS tutorial is thinking about sort of the overall scaling frontier of uncertainty and robustness. In particular, if you're trying to plot something like the number of parameters or some level of compute on the x-axis, and you're measuring on the y-axis some quantity for uncertainty or robustness. It could be the deferred prediction metric that's used in the last slide's task. It could be how well you're able to detect out of distribution inputs, or how well are you able to adapt quickly to new examples for a few-shot learning case. So any of those cases, you're looking at how well my model performed as a function of compute. And what we'd really like to do is try to trace out this frontier, as we do have a strong sort of hypothesis that the more compute that you do have will in fact help for both of these properties. And that in the overall sort of AI frontier, it's not so much about trying to improve IAD test set performance, but you're trying to improve the overall reliability of these models as it's applied to different interventions applied to the data, as you're trying to make actual decisions with your model, all this sort of stuff. There's a few different directions that we've been exploring within the team that have, I guess, focused on that overall frontier. And just to give a lightning overview of those before we go into the infrastructure, one of that we really found vital has been sort of the idea of combining multiple predictions. So we call this ensembles. It could really be more broadly Bayesian neural networks, or anything that's allowing you to combine those multiple predictions. And we found this across different works where as you're applying these multiple predictions and in specifically developing efficient ensembles or efficient Bayesian neural networks, you're able to actually have models that for a given number of parameters, you are outperforming the, base architecture that may have been scaled up by however many times.
Sorry to interrupt, Dustin. There is a common question in the Q&A. Can you see it, or shall I?
Let me see if I can find it. Oh, okay, I see it. To clarify, you mean uncertainty is about your prediction or something else? So in most cases, I mean predictive uncertainty. So the uncertainty is most likely going to be in a classifier, your softmax probabilities that are going to be the outputs. In other cases, you might use a different form of uncertainty. So they're in different decompositions. There might be just model uncertainty, which is uncertainty about the specific function that you're trying to model. In other cases, it might be aleatoric or data uncertainty. But yeah, most of the time, the work that we're talking about is predictive uncertainty. Okay, a crucial element of this has been ensembles. And so when we'll be talking about infrastructure, a big part of it will be thinking about how we develop uncertainty models to address the different models that we like to iterate on the research side. Another component of this that we found pretty vital most recently has been just the scale of the models. So in validating that sort of frontier that we've been thinking a lot about, one thing we found is that the scope of large pre-trained models really does have an impact on uncertainty performance, whether it be calibration errors, so that's a left figure, or out of distribution detection, which is a right figure. So in these cases, there's sort of a common belief in the literature, which is that deep neural networks tend to be very overconfident. And in particular, as you scale up, so you get deeper neural networks, wider neural networks, your models are becoming more and more overconfident. So they become more miscalibrated, or they perform even worse on out of distribution detection. However, in this sort of paradigm of pre-trained models with slightly different architectures, with things like vision transformers, with architectures that remove all convolutions altogether, there's an interesting note where you actually can get sort of the best of both worlds in getting not only really good accuracy, but also really good uncertainty scores. So there's a lot of incentive to really think about the effects of these different models at scale. Okay, and I see another question, what I mean by frontier. Well, so a common question in deep learning is really about, or I guess a very fundamental axis that many people have been exploring is really about frontier as a function of compute. So if you're you're trying to do something like get state-of-the-art performance on image classification benchmark, or get the smallest bits per dimension for compression for some language modeling task. Well, the usual way people do it these days is just take some base architecture that works really well and scale it up as high as possible. So they're really trying to map out the frontier and get this sort of test set performance. What we're sort of arguing here is to not only do that for test set performance, but really care about the reliability properties of the model, examining the uncertainty quantification, examining the robustness metrics. And I think we'll talk a little bit more about those detail later in the talk. Okay, I hope that answers the question. Feel free to raise more. So just to give an overview of how different components in our infrastructure fit into our research workflow, here what we're showing is sort of a diagram of how all different processes you might do in training and evaluation and building models fit into different frameworks. So first, a big component of this is just trying to build these large models with different layer components, with different regularizers, with different initializers. So that's the point component where we're using the Edward2 browser programming language to iterate with like different ensemble models, different base architectures, all that sort of stuff. And what Zach will be talking about is uncertainty baselines, which is really this large experiment code base with a lot of nice components to do iterative sort of training and reproducing from scratch from instantiating the models all the way to launching the training jobs to actually reproduce results and get strong performance. There's a final component of this that we won't be talking about in this specific talk, and that's around just evaluation. So given, say, a checkpoint, given like a model that's been trained on either a massive pre-training data set or just some typical thing like CFAR, a component is sort of out of distribution evaluation. So it's taking those models and evaluating it on different shifts. For example, the ImageNet-C that I was just mentioning beforehand. And the goal behind really trying to develop the infrastructure for this overall pipeline is to build an experiment template for researchers. So this is really targeted toward the uncertainty in process research is really targeted to ourselves in the team. And we've tried to make this as sort of modular as possible so that different folks can use different components as needed. If they just want a really strong baseline that they can compare against, that they can build upon, then there are very specific scripts that you can try to grab to get a really strong ensemble performance, for example. Okay, so I'll give a very lightning overview of Edward2, and then I'll hand it over to Zach to talk more about the maybe more interesting component with uncertainty baselines. Okay, so in Edward2, there's really just sort of one major component that we're thinking about, which is taking an existing numerical ecosystem and thinking about how to incorporate a notion of random variables in there. And in our case, what we do, is take a specific primitive that's operating in a particular language and associating that as some form of a random variable. So in the case of TensorFlow distributions or TensorFlow, we take the typical distribution that you might have, and under the hood, we're actually associating each of these class objects with a particular instantiation of the value. And so given these sort of objects, you can actually do some more fancy operations on them. So just sort of an example of different distributions or random variables you might have. Similarly, in NumPy and SciPy, this is actually how you operate, where you take, say, a different generative process that you might get for a particular distribution. That's exactly how we instantiate random variables in those cases. And maybe how to fit these things together. Well, when we're thinking about probabilistic programs, they're really sort of a composition of deterministic operations on these random variables. So in this case, as an example, I'm just showing sort of a linear model. So you're taking some input X as which are the features or the covariates as inputs. And then you have some prior over your weights. And the output of your linear regression model is going to be some matrix multiplication. Here it's an einsum of your beta terms with your actual inputs. And then here we're assuming it's a homogeneous model, so the scale is just 1. And given that program, so this function here represents the generative process. It conditions on specific inputs. It's the covariates. It returns specific outputs that the probability distribution is over, so P of Y given X. Given that sort of model, you're able to do all sorts of weird, fun stuff with it. That's actually the important thing for probabilistic inference. So if here, although in this function, we've represented something like a generative process, you can do things like get the log joint probability function, and that's important for different variable inference or MCMC tools, for example. To fit this into the different neural networks that we're thinking about, well, this is just sort of a recap of how neural networks work in most languages, where they're decomposing in just a composition of different layers, and those layers are just these parameterized functions over some set of real arrays, different tensor values, and there's different sort of components or different semantics behind how these layers work. There's things like initializers, there's things like regularizers. These are also just sort of functions, and then initializers are giving you the actual initial values. Regularizers are about things like L2 penalties. What we're trying to do with Edward2 specifically for neural networks is to enhance the overall semantics with additional randomness. So if you're thinking about neural networks like Bayesian neural networks or other types of uncertainty models, Well, you can actually take that notion of a random variable and augment the neural network layers with different components. So for example, if you're changing the weights of a neural network so that instead of having these deterministic tensors as the weights or the hidden units as deterministic tensors, and you make them random variable instead, then now you immediately get Bayesian neural network layers. Similarly, if you have the entire function as random, that's how we actually implement Gaussian process layers. And you can do this sort of thought exercise for all different states in the overall computation of a layer. If you have output as random, you get stochastic output layers that return a distribution. You can even get reversible or like flow or normalizing flow type of layers, where if the input is itself a random variable, then the layer is sort of like a transform, it returns a transform distribution. So if the reversible layer is in fact a one-to-one mapping, then you're able to actually get the exact output. And that's useful for different generative modeling. And I think this is sort of a core property that a lot of people started to adopt for Bayesian neural networks and GPs. So I think I saw interesting work from GP Flux that was capturing very similar properties as this. Okay, and to give, I guess, a very brief example how this works, here, this is just like a very quick snapshot of how you're to try to do something like a Bayesian LSTM from scratch without any sort of abstractions. It's quite tedious. You know, you're defining a model, you're defining a variational family, you're manually, controlling all the different operations, all the different variables involved. If you use layer abstraction, then it's sort of just raw keras. So here we just have a version of a variational LSTM cell, and you use your typical keras to loop over different inputs, train the model. Similarly for ResNet 50, this is just a vanilla implementation where you might have different blocks for different neural network layers. And the variational version is as simple as just changing, say, the convolutional layers to be variational dropout layers or any sort of ensemble layer. Yeah. Okay, so now I'll hand it over to Zach to start talking about uncertainty baselines and how that how the Edward2 part fits into the overall experiment pipeline.
Cool. Can you hear me?
Yes, I can hear you.
Okay, great. Okay. Let me get back to the beginning. Cool. All right, can you see this?
Yep.
Yeah, that works. Yep.
Okay. So I'm Zach. I work with Dustin at Google Brain, and one of the projects we've been working on together lately has been this uncertainty baselines code base. And we have a preprint write-up about it on Archive if you're interested. And we also the main place to find it is on our GitHub repo, which will be linked to throughout the presentation. And so uncertainty baselines is the code base that we use for a lot of our research internally, and now with some joint external collaborators as well, regarding the very interesting uncertainty and robustness stuff that Dustin was discussing previously. And so this is kind of like what enables us to scale to those like very large model sizes and data set sizes and numerous evaluations and all of that. And a lot of it is these cloud launching pipelines and experiment configurations and data sets and models and all of the kind of glue code that goes into setting up those pipelines. And we have several goals for this, where obviously we want to be able to reproduce our previous work in all the papers we've been publishing as part of this research effort. We also want it to be very easy for people to take our baselines and then build off of them to do new, interesting, novel research as well, and make it as like easy to do an apples to apples comparison with our previous works, because there's so many papers coming out nowadays that it's like hard to compare them sometimes. And so we want to be able to give people, you know, either very easy ways to compare to our previous results, or, you know, jumping off points to make easier to compare to work for us as well. And so this is a subsampling of some of the public papers that have come out of this code base. All of the links will be in the slides that we release later. And a lot of them are, you know, as you can see, something regarding improving the predictive uncertainty of deep neural nets, or measuring it, or, you know, other ways of exploring it. And we've also used it for several Google internal products about, you know, they kind of have used our code base to experiment with ideas for these production systems on improving predictive uncertainty, especially under distribution shift, which is, you know, a big problem for any production system nowadays. Cool. So yeah, like a lot of this uncertainty baselines code base is about, you know, taking Edward2, which is what we use for a lot of our, you know, Bayesian layers and stuff, and scaling it up to like very large cloud, like billion parameter pipelines. And so a large part of that is testing, and we want to be able to move fast and not break things. And so we want to be able to have confidence when we are, you know, rapidly iterating and adding features to our code base. And so testing deep learning code, as I'm sure everyone here is painfully aware, is painful. End-to-end tests, you know, they're great if you can get them to work, but sometimes due to non-determinism, whether it be through like firmware or other driver updates, can really make them flaky. And not only, even if you can solve that, they can be very expensive to run. So like, you know, several of our workloads take like many dozens of GPUs or TPU cores, and can take like, you know, multiple hours or days. And so always having to pay internally the bill for running all these big end-to-end tests, you know, sometimes might not be worth it. And so instead, what we've kind of done a little bit of a compromise, where we have unit tests for the majority of our code base, where usually it'll be simple little smokescreen tests of just like, you know, checking the shapes and D types and like ranges of values of either model outputs or data set batches and all of that. And if you don't use it already, I highly recommend everyone here use PyType. It's like natively supported in Python 3, and it has caught, you know, a lot of just very simple type errors during development, and it is making Python code much more self-documenting. We also have some quick training tests that basically will just like, you know, train a model for like a dozen steps or so, just on a CPU. And then we check the loss after several steps to make sure, you know, the whole kind of code can be exercised and it will run end to end. And so in order to enable those tests, though, if you want to have any meaningful, you know, confidence in your values coming out of it, you need to have determinism. And so something that I've been very happy that JAX has popularized has been splittable and foldable RNGs. And I highly recommend everyone go and read about how JAX does their random state handling, because I think it's phenomenal, and it's how probably everyone should do it, because it makes deterministic code by default and is very easy to follow kind of once you learn the two little idioms of the API. And so, you know, of course, given the same hardware and software versions of our drivers, we do have some deterministic baselines in our code in TensorFlow and JAX. Cool. And so in addition to TensorFlow and JAX, we also support PyTorch. And I don't want to get into, you know, a flame war about which one is best. So we kind of decided we would support all of them. And I'll get into later about, you know, how we enabled this, but obviously Google has a lot of our tech stack built on top of TensorFlow, and we want to keep being able to serve people internally and work with a lot of the existing infrastructure we built up in TensorFlow, which is fantastic. Except when we were collaborating and talking to external researchers, a lot of them were like, I'm only going to use PyTorch. And internally, and in some maybe Google adjacent research circles, everyone is starting to really, really love JAX. And so we've also been moving more and more towards a JAX-oriented code base, but we do have a lot of TensorFlow and some PyTorch code in there as well. And so all of our TensorFlow code is TensorFlow 2, and one nice thing is all of our data pipelines, because TF data allows you to just output an iterator over NumPy arrays. We can reuse the same data pipelines for all three of these frameworks, which reduces what would have been a lot of redundancy between them. And so a lot of code bases, will, in terms of project structure, have some standalone models and data sets, directories that are pretty reusable and self-contained. But in my experience, at least, where a lot of the interesting debate happens about how to structure the code base is, how do you structure your training and evaluation parts of the code? And so I kind of view this as like a spectrum, where on the one end you have like every single experiment you want to run has to like re-implement like the main function. Like it has to like totally re-implement all of the training and eval loops and code. Then you kind of have a middle ground of some shared training and eval code for common use cases, like, reusing common training loops or like evaluation pipelines. And then on the other end, you have stuff like TensorFlow Estimator, which I don't know if people are familiar with here, but I am unfortunately familiar with the TensorFlow 1 days, which had a very, or I guess this would also be like, Keras model.fit would be maybe a more relevant example. But, you on the farther end, you have this kind of everything is baked into one magic function that's a black box. You just like give it a data iterator and a model and it will train it. And it's like some abstracted API. And so Uncertainty Baselines took the route on the other extreme of everything is a standalone script for all of our workloads. And to us, this was really, it worked out very well, because for a lot of our experiments and workloads, we have very different training and eval loops. So we might have to do like weird pre-training phases for some of the experiments, or we might need to do like very customized training loops where like different steps have different graphs that are run on each one. And so trying to abstract all of that away into something that is very generic would have been extremely painful and probably not worth it. And so that's kind of, one of the pros to this, I think, is that there's no dependencies between the experiments, and you can do whatever crazy stuff you want to do in your training loop and it won't affect anyone else's abstractions. And it's very easy to go in, and if it's just like, oh, you only want to run like the batch ensemble code on ImageNet, then you only need to look at like that particular script, and that's all you need to fork, and all you need to learn end to end how it works. Some of the downsides are that we do end up repeating a lot of code, and if we want to do like a code base wide refactor, it can be a bit of a pain, although I've gotten very good at regexes in order to solve this problem. And it also can make our tests a bit longer to run, just because we have to have more individual tests for different training loops. But I do think that is the pros do outweigh the cons here, at least for our code base. And so if you do check out our GitHub repo, you'll see something like this in an abbreviated form. And so we kind of have like two halves of the code base. One is the Spacelines directory, which contains all of the training scripts and experiment configs per workload that we run on. And so you can go in here and, hit the ground running to reproduce a lot of our previous papers. And then we have our uncertainty baselines, which has a lot of the kind of like library code around supporting these different baseline scripts. And so, like, for example, we have a quasi-random sequence generator in here to reproduce exactly how we did all of our hyperparameter tuning. We also have all of our TF data pipelines, and we also have all our models. And so our data sets are in TF data, which I think is a great API. And many of them are even hosted on TensorFlow datasets. And so some of them, obviously, like imaging, you have to manually download, but a lot of them are just like out of the box, will run right away in a collab, which I think is great. But in addition to that, we have several data sets that are a little bit more niche. And so we also have an API for implementing custom and local data sets. And one of the really powerful things about TF data, in my opinion, is it allows for very efficient pre-processing parallelism on the CPU. And it can like really take advantage of like a multi-core setup, like in a beefy GPU or TPU machine. And so the way that we define this API is just by requiring someone to define a pre-processing function and and also a loading function, but that's going to be guaranteed by default. And so to use it, I guess like the API that we came up with was something like this, where you set up some building object and then you call load on it and you give it all the information you need. There's a little bit of a ugly thing here where for TensorFlow multi-host training, they used distribution strategy API. And so we have to pass that in here as well. But at the end of the day, you can just get your iterator of NumPy arrays and then do whatever you want with them. And I know that there's some tricks in there for avoiding copies if you're using something like PyTorch or JAX, because in TensorFlow, they can compile the whole graph together. PyTorch and JAX, a little bit more nuanced, except we have examples that take care of that. So speaking of, different frameworks, we did not want to go down the rabbit hole of making a framework agnostic model API because there's multiple facets of deep learning models nowadays that each individual framework takes care of for us, such as device placement or jitting or autodiff. And, I didn't want to have to reinvent the wheel yet again. And even within each framework, at least within JAX, I know there's several different competing frameworks for how to build your models. And so we were just kind of like, we don't want to get involved. So we're just going to make one function in each of our model Python files that returns either a Keras or PyTorch or Flux model. We've chosen the JAX Flux model library just because they kind of sit closest to us in the org chart. And so they can help us out the most with stuff. And I really, really do like that very clean Pythonic library Flux.
Sorry to interrupt, Zach. There is a question.
No.
Can you see the question?
Yeah. Yeah, so I guess this is maybe also Dustin could answer this, but in terms of, this seems like data input uncertainty, if I understand correctly. And so we definitely are interested in looking at things like label noise and things like, I guess like some sort of other uncertainties in the inputs, but a lot of our work has been more on the output side of stuff.
Yeah, I would agree with Zach that I think most of the work that we've been doing has been, or like any data uncertainty that we look at has been like, say, examples where the specific prediction, the specific label that you're getting is not the ground truth. And this appears even in core deep learning settings like classification. The labels you get for standardized benchmarks are not even the hard labels. They're often wrong because they're an aggregation of multiple raters into one specific hard label. And then even in like translation, these are happening. In the input space, there are natural analogs that we could apply similar methods to. And this happens quite often, as you're noting, especially in things like missing data, other properties of other properties where the image itself that you're gathering may be quite noisy, or the features you're gathering might be quite noisy.
Yeah. Cool. Can you see my slide still?
Yes.
Yep.
Cool. Okay. So the other kind of big component, or one of the other big components of our research, has been on metrics. And so, it's great and all if you can launch your job and train and eval and everything, but really we want to be able to measure exactly how our model is performing, both in just a raw accuracy and loss perspective, but more particularly and like how is our model behaving under dataset shift in terms of like graceful degradation and uncertainty quantification. And so we don't define our own metrics because that kind of seemed like a endeavor in and of itself. And so there's this other project within Google Brain called robustness metrics. And so they have many framework agnostic metrics that are all in NumPy. And so they also have eval pipelines that do a little bit of abstraction of the eval loop on numerous test sets that we sometimes use as well, which are very well done. Highly recommend going and checking them out. And again, the more generic API for metrics is you just have to define some add predictions or batch of predictions and then result. And so this is really important for some metrics like expected calibration error, ECE, which is one that we use a lot, where you cannot trivially decompose it element-wise within your batch. Like you actually have, or like AUC, for where you have to have these intermediate variables that you accumulate, sometimes even in a multi-host setting. You have to make sure all your synchronization is correct. And so robustness metrics has done a great job of getting all that done for us. And so to me, where I think some of the real power of these sorts of code bases comes in is when you figure out things like nice experiment configuration, because like, again, a lot of people have well done models and data sets and all of that, but how easy is it to kind of hit the ground running with a new pipeline? I think is one of the tests of these sorts of code bases. And so I personally have recently, due to some NeurIPS rebuttaling, been going back and forth with reviewers about different experiments we did, and getting more data, or like reslicing the data or rerunning things like slightly different ablations. And the only reason we were able to do that is because we had all of our experiment configuration files checked into our version control system. And if it weren't for that, then we would be totally dead in the water, because checking in all these experiment configs, I believe, allows you to then go back and see exactly what was run on exactly what hardware with exactly what hyperparameters, and then you can trivially fork it, try out something else, check it in, and run it. And different people have different philosophies for what these configuration files should look like. I've seen shell scripts that just have the exact command with a whole bunch of flags to launch it. I've seen Absol is a flags and like binary running library that we use a lot. And so there's like files to configure the flags for that. Sometimes people just have a big README comment section on how to reproduce the experiments, which also works. You can choose your own adventure here to some extent. And so we use Python files actually that return a lightweight wrapper around a Python dictionary. And the reason why we use a Python file is so that we can parameterize our experiment configs. And so this is super useful if we want to do something, for example, if we want to run like the same workload on like 10 different data sets, or if we want to run, 5 different model sizes on one data set or something like this. And so we can, and there's some, complex logic that has to be computed for every single ablation, then we can do that in Python and come up with the exact config for each. And And so we will hopefully very shortly, once some approvals go through internally, be able to open source our cloud launcher, which takes these experiment config files, runs them, and then just sets up the flags key values to pass to all of our individual training and eval scripts. And so, yeah, these flag values then are kind of what drives a lot of our hyperparameters. And so besides the training and eval code, I think that one of the other more opinionated parts of a deep learning code base nowadays is how do people manage their hyperparameters. And so some people will just dump them all into some nested dictionary and pass that around as just like hparams, or they'll come up with like some custom Python object for that. I've also seen dependency injection frameworks for, you know, adding function decorators that will auto-magically grab the correct values and put them in as arguments. Some people like to just use the global flags values throughout all of their code. Some people will write out every individual hyperparameter as an individual keyword arg in every function. And again, you can, you know, come up with dozens of different solutions to this. But so I recently asked on Twitter about, you know, how people do this, and I got responses that covered the majority of this list. And so the one that we chose was to use just individual flags for each of these hyperparameters. And so for some code bases, I do not think this would be a good idea. However, for uncertainty baselines, it actually works out quite nicely, because even though I think the biggest con of this is that it's very verbose, because you have to define an individual flag and then keyword argument for every single hyperparameter you want to tune. Because we have standalone training scripts for each of our experiments, we actually don't have like arbitrarily deep nested libraries of functions that we have to pass this down through. And so like if you had something where you had like a more abstracted training and eval loop, then you might have like several functions that have like really, really deep keyword argument lists that you'd have to pass stuff through. And I think some of the really nice things about this approach is that it's very clear how every hyperparameter is treated in the code, and it's much easier for some newcomer to go in and understand that or fork the code and modify how the hyperparameter is treated. But yeah, so that's it for uncertainty baselines. Please, if you are interested in contributing or trying it out, you can go to our GitHub page. If you just Google uncertainty baselines, it'll come up. And, you know, file an issue or PR, or email us if you're interested.
Cool, thanks for that. Yeah, that last section as well on the try to like rerun things with different settings and stuff. That's, I'm sure we've all been there and like had various levels of success and disaster in that. Like, so that's really appreciated.
Yeah.
I don't know about anything else, but that's something I'm going to look into. I don't know whether we've got time for questions. I can't